So far, we have realized why our equation was a good and flexible way to deal with the complexities of having a categorical variable as a dependent variable. And we got a qualitative sense as to how a change in beta 1 and beta 0 would change our curve. But we need a little math to get a quantitative sense of how beta 1 and beta 0 could affect the curve and what the mathematical interpretation of beta 1 and beta 0 is. In order to do so, we can rewrite the equation of probability and solve it for the exponential, or e to the beta 1x plus beta 0, which turns out to be simply p divided by 1 minus p. This ratio, the probability of something happening divided by the probability of not happening, is usually called the odds. I believe it makes sense to spend a minute getting comfortable with the concept of odds before moving on. So here we have a table with just some numbers for probability and some numbers for 1 minus p, and then if you calculate the odds as p divided by 1 minus p, we will have these numbers. As you can see, for a probability of 50%, 1 minus p is going to be 50% again, so 0.5 divided by 0.5 results in an odds of 1. So what this means is that as long as odds are more than 1, the probability of that thing happening is more than 50%. So anything with odds of less than 1, of course between 0 and 1, it means that the probability of happening is less than 50%. Now that we are a little more comfortable with what odds are and how that relates to p and how an increase in p results in an increase in odds, let's rewrite this equation in terms of odds. Looking back at this equation, we can rewrite it as p over 1 minus p, or odds, equal this equation, and then we can further expand this into e to the beta 0 times e to the beta 1x, or further expand it to odds equal e to the beta 0 times e to the beta 1 all raised to x. Now, why is this a useful representation of this equation? Well, let's give an example. What happens if x equals 2? Odds of x equals 2 would be e to the beta 0 times e to the beta 1 times 2e to the beta 1. What happens if we use 3 for x? So the odds would be e to the beta 0 times e to the beta 1 times e to the beta 1 times e to the beta 1. So what is the difference here? By a unit increase in x, the odds was multiplied by e to the beta 1. Now, this always happens even if x is not an integer. So what we have in general is that odds of x equals n plus 1 is going to be e to the beta 1 times odds of x equals n. Or again, in plain English, by a unit increase in x, the odds is going to be multiplied by e to the beta 1. So this is a very good interpretation of what beta 1 is. Now, how about the interpretation of beta 0? In order to get e to the beta 0, you have to set equal x to 0. So what happens is that odds at x equals 0 would be e to the beta 0 times e to the beta 1 raised to 0, which equals 1. So one interpretation of e to the beta 0 is that it's going to be equal to odds at x equals 0. Now, by looking at this expression, we can see that now we have a good sense of what this p over 1 minus p, or odds, means. But the left side, it's a little too complicated. What does it actually mean, e to the beta 1x plus beta 0? Now we can make this part a little easier, but there's a compromise. The other side would get a little more complicated. So how we do that is to take the log of both sides and then set them equal. Log and e would cancel out because they're inverse functions, and we would be left with log of p over 1 minus p, which is log of odds. So although as promised, the other side is much more simple. It's just a linear relationship between log of odds and x. This side, we don't even understand what log of odds is. So in order to get an understanding, we would go back to our table, but with the addition of one column namely log of odds. So we remember that for any p, we could calculate 1 minus p, calculate the ratio, and that would be our odds. And then if we take the log of this column, we would be left with log of odds. Now, you remember that this was a critical point. A probability of 0.5 would result in odds of 1. Now, the log of 1 is 0. Any probability less than 50% would result in odds of less than 1, which would result in log of odds with a negative value. And any probability higher than 50% would result in odds larger than 1, which would result in positive values for log of odds. The important takeaway from this table is that this 50% probability is a critical value here because it will result in an odds of 1 and log of odds of 0. And there's another thing that you need to remember is that an increase in probability would result in an increase in odds and an increase in log of odds, and equivalently a decrease in probability would result in a decrease in odds and a decrease in log of odds. Going back to the newest version of our old equation, we can see that there's a new interpretation for beta 1 and beta 0 based on this format. So repeating what we did before, calculating the log of, this time the log of odds for x equals 2 and x equals 3, we can see that a unit increase in x would increase the log of odds by beta 1, or in general, log of odds at x plus 1 would be the log of odds at x plus beta 1. And what about the interpretation of beta 0? So we should just set x equals to 0 again, and what we're left with is beta 0 equals log of odds when x equals 0. So this is a new interpretation of beta 1 and beta 0.